Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on identity and inverses. So we're going to go through what they actually are. So although identity and inverse have the same meaning regardless of the operation, the numbers turn out to be slightly different depending on the operation. So first what we're going to do is look at identity, but we need to do two different cases. We need to look at multiplication and addition. So you might be wondering why I chose these particular operations. It's just because we're going to come to look at things like groups and rings, and in, say, a ring, multiplication and addition are the operations that determine whether or not it is a ring. So we're going to look first at the identity in both multiplication and addition, and it turns out to be a different number for both. So I just want to quickly make sure you know what I mean when I say element. So element just means the member of a set. So we learned last time that in mod 4, there are 4 elements, 0, 1, 2, 3. So when I'm looking at the set of integers modulo 4, there are 4 elements. 0 is an element, 1's an element, and so on. So I'm talking about an identity element here, a member of a set. So for both multiplication and addition, to illustrate these points, let's say I'm looking at the set of all real numbers. So what is the identity element of the set of real numbers? Well, for multiplication, the identity is 1. So why is 1 the identity? So we get this name identity because it preserves identity. So in the field or the set of real numbers, any real number A, so this notation means A is a member, an element of the real numbers. If you multiply A by 1, you just get A. Or if you multiply 1 by A, you just get A. So it's called identity because it preserves identity. When you multiply by the identity, in this case 1, it does not change the element. The element stays as it was before you multiplied by 1. So for addition, the identity is not 1, because if you add 1, that will change the number. The identity is actually 0, because if I have another element of the real number, so x is just a real number, if I add x to 0, it doesn't change it. If I add 0 to x, it does not change it. So what we do is we say that 1 is the multiplicative identity and 0 the additive identity. So again, we call something the identity because when you operate with it, it doesn't change the identity of what you started with. So in addition, if you add 0 to something, it doesn't change the identity of the thing you added 0 to. So that's why it's called an identity. So now let's look at an inverse. So colloquially, inverse means to undo something. So in maths, we say an element is an inverse if you can operate with it to get back to the identity, either the multiplicative identity or the additive identity. So just as we saw before, the elements will be slightly different if they're a multiplicative inverse compared to if they're an additive inverse. So let's formalize this. So let's say we have 2 elements of the real numbers A and B. So they're just normal numbers. So we say B is an inverse of A if A times B gives you the multiplicative identity, or B times A gives you the multiplicative identity. So of course here, if B is an inverse of A also satisfies the definition for being an inverse of B. So they are inverses of each other. So one thing I just want to point out, in case you do more reading, it's a little confusing, but if the set you're talking about has multiplication, but multiplication is not commutative, this and this may not be equivalent. So one of them may be true, but the other false. And that's where you get the terms left and right inverse from. But we're going to be looking at mostly commutative things where the order of multiplication doesn't matter. So both of these will be true when multiplication is commutative. So that's what we mean by inverse. So similarly for addition, if I have, let's say, two elements now, x and y, that are real numbers, so they are said to be inverses of each other if when you add x and y, you get the additive identity, or when you add y and x, you get the additive identity. So we say that they are additive inverses because this time they don't multiply to give 1, they add to give 0. So let's look at the real numbers and look at what some inverses are. Just quickly though, I want to make sure you're aware of some notation. We usually write the inverse with a -1. So s minus 1 usually means s inverse, but multiplicative inverse. And we usually write minus s to be s inverse, but this time we're talking addition. So in our previous examples, A was the inverse of B. So we might write it like that. A is the multiplicative inverse of B. Here, we say x is the inverse of y. And it's pretty clear, I'm sure, why we use that notation. All right, let's go and look at some examples in the real numbers. So let's start off with the number 1. What's its multiplicative inverse? Well, its multiplicative inverse is itself, because you multiply 1 to get 1. It's already the multiplicative identity. So what would its additive inverse be? So what do you need to add 1 to get 0, which is the additive identity? Well, that would be -1, because 1 plus -1 is equal to 0. So let's look at a number like 4. What is its multiplicative inverse? What do you multiply by 4 to get 1? So that is 1/4, because 4 times a quarter is equal to 1. Notice that a quarter is 4 to the power of -1, just like 1 is 1 to the power of -1. So that's why we use that notation. When you times a number by that number to the power of -1, you get the multiplicative inverse. So what's the additive inverse of 4? Well, that's easy. That's just -4. What if we had something like -2? Well, its multiplicative inverse would be -1/2, because 2 times -1/2 is equal to 1. So that turns out to be -2 to the power of -1. So the additive inverse of -2 would be +2, because -2 plus 2 is equal to 0. So what if I just had a general fraction a over b? Of course, here b can't equal 0. So what do you multiply by a over b in order to get 1? So you just flip the fraction. A over b times b over a is 1, but this time a can't equal 0. So what would be the additive inverse of a over b? Well, that's easy. It'd just be -a over b. How easy is that? So let's look at the number 0. So 0 is a special case in the real numbers. It does not have a multiplicative inverse, and it turns out that it is the only real number that doesn't have a multiplicative inverse. That's because you cannot times 0 by any number to get 1. So we just say it has no inverse. Of course, 0 is its own additive inverse. Just like 1 was its own multiplicative inverse, 0 is its own additive inverse. So I just need to explain one more sort of special case. So that was all well and good for the reals. Let's just look now at the integers, which we usually denote z. So that means integers or whole numbers, and it does include 0, it does include negative integers too. So let's now look at the element 4. So what do I times by 4 to get 1? Well, I told you before that I times 4 by 1/4 to get 1. But hang on, 1/4 is not a member of this set. 1/4 is not an integer. So even though 4 has a multiplicative inverse in the set of real numbers, it doesn't have a multiplicative inverse in the set of integers. So if we're looking at the set of integers, 4 does not have a multiplicative inverse. It does, however, have an additive inverse, which is still minus 4, because minus 4 is an integer. So I want to make that point. If we're not talking about the real numbers, if we're talking about some subset, including if we're talking the integers modulo m, not all elements will have a multiplicative inverse, because the thing you multiply by to get back to 1 will not necessarily be in that set. All right, I hope you found this video informative. This has been the luckiest maths teacher in the world. Have a great day.